So, thanks to Mikkel for putting this summer school together. I guess Mikkel contacted me a few months ago and said, you know, could I come to this summer school and give a talk? I said, of course, what do you want me to talk about? And Mikkel said, oh, you know, streams, sketching, databases, that kind of stuff. So then I looked at the program a couple of weeks ago and I saw that my talk was listed as streams, sketching, and databases. I thought, well, I have to make one correction to this. Right? We don't say databases anymore. Right? We say big data. And you know, I've been working on this topic long enough that I remember 15 or so years ago when we called this topic massive data. Now it's gone from massive data to big data. So there's a serious point under here, right? That when we started looking at massive data, it was sort of this sort of slightly focused view of, you know, viewing the world as a vector and looking at all the kind of ways you could capture information about that vector. And this kind of buzzword big data that you hear at every workshop or summer school you go to, you know, behind all that buzz there is something reasonably serious, which is we're in a situation where data is the quantity that's growing, right? You know, the N is getting bigger, and that's happening from a wide variety of different applications. This happens in, you know, science, where people are sort of measuring what happens when you smash subatomic particles into each other. It happens in medicine, where we're capturing more and more information about the vital signs of people. It happens as we sort of walk around the world and we're all carrying these little GPS devices that record where we are and what we're doing. Businesses, you know, Mikkel talks a lot about the kind of things we looked at AT&T, but, you know, Facebook, Google, Microsoft, Amazon, and every other business that has any kind of technological aspect to it is trying to capture all kinds of information about you. So we're in this sort of world where these sort of themes are emerging, that we've got lots of data, it's large and it's getting bigger. We want to do things to this data, we want to understand what's going on in this data. There are important patterns and trends in this data. And it's kind of an exciting time to be, you know, a researcher, because we don't have the answers yet. We don't know how to find all the patterns and structure in the data that we want. We don't even know yet what are all the kinds of patterns that we want. You can come up with a new idea of a new quantity or a new measure and define algorithms that will help you find that efficiently. Okay. So, you know, moving towards what are the kind of algorithms we want to support, we want to take this data, and for most of this talk I'll be sort of looking at data in a fairly abstract way, so we're not going to make it too specific about any application. And you want to interact with that data in a variety of different ways. So one way is that, you know, you have a company, it has some sort of weekly, daily, monthly reports that they want to run on their data to pull out information about that. As well as big data, another buzzword that we hear a lot about at the moment is data science, right? And that's sort of the people that interact with the big data using the kind of tools that we're going to build for them. Right? So you want to allow these data scientists to start interacting with data, kind of form hypotheses, test them out, run them, and quickly get answers to their questions. You know, did we sell more products in this region than that region? If we break it down by age, what kind of patterns do we see? These kind of ad hoc analysis questions. You know, there's also situations where you want to sort of monitor what's going on. You're seeing lots of information coming along, and you want to sort of quickly track when things change, how things change, get kind of alerts. And this sort of, you know, old term of data mining from the 80s is having this resurgence now. Again, it's sort of saying treat the data sort of offline as this huge quantity of information. What kind of patterns and knowledge can we extract from that? So in order to do any kind of these things, we need to build algorithmic tools that will let us answer primitives over large quantities of data very quickly. Right? The kind of basic things we need is to say, well, we have this huge wad of data. How do we understand what are the distribution of particular attributes within the data? If the data is, we think of it as a sequence of transactions, how many distinct types of different things did we see? Or when we subset on particular quantities, how many different things did we see? How many, you know, x's that meet some condition? How many objects smaller than some value y, or, you know, having some particular combination of attributes did we see? Can we sample? Can we pull out values from the data? So these are kind of the algorithmic questions that we're interested in when we talk about big data. And, you know, because this is summer school on hashing, I'm going to talk today mostly about how hashing techniques So, where is sort of big data and hashing? Where is this intersection? So I'm going to sort of try this characterization that says, well, when we think about traditional hashing in an algorithms class, we learn about hash tables, linear probing, these kind of things. So you're storing data exactly, and it's primarily so you can do fast lookups and updates. It's relatively compact because, compared to the size of the universe you're drawing items from, you're just storing information proportional to the size of the data. But you're doing things exactly. And then, over the course of the last couple of days, we've seen examples of sort of exact storage, but we've also seen examples of this sort of inexact storage, things like Bloom filters, where we're trading off. We're no longer exact, we're sort of more into probabilistic storage of information. We're tolerating some amount of errors in the form of false positives to make us faster and compacter. And so what I'm going to talk about today is sort of taking this a step further and saying, let's go from hashing where we sort of accept that there are some collisions to hashing where collisions are inevitable, and what we do is we understand what these collisions mean to us mathematically in terms of the description of the data. So this is a world of sketches, where the word sketch means many things to many different people, but for me it's this sort of compact representation of data, where typically we're using hashing to define that representation. That hashing is allowing, in fact, encouraging collisions to happen, but the underlying signal that we're trying to capture from the data is preserved through all this. So, I said Bloom filters are sort of faster, compacter, so I'm saying sketches are even fasterer and compacterer compared to those. So it's this idea that we're trying to build a summary of data. Okay. So, one of the other keywords in the title was streaming. This idea of streaming is to say, can we not only do all this, compact representation through a sketch, but can we do it when we see data sort of incrementally? So we don't sort of see this nice offline lump of data that we can sort of have random access to, that we can search, we can sort, but rather we're just presented with the data incrementally, piece by piece. And, this is implicitly the kind of model that we've seen a lot already. The model of processing updates to a hash table is really one where you don't know what's coming next, typically, and you try and just cope with every update as you see it. The model of Bloom filters is exactly this, that items arrive and you just process each update incrementally. So they shouldn't be surprising. And again, thematically, what's happening is we're seeing problems where often the original problem, the actual underlying problem we're trying to solve, doesn't seem that difficult if only we could store all the data. And the reason that these problems are difficult is because we're seeing just a huge volume of data, that those sort of traditional solutions, if step one of your solution is sort the data, that solution doesn't work. So we're having to come up with new approaches. Okay. So two models I'll be working with today, just to distinguish an arrivals-only model, often called cache register model, where we see a sequence of tuples that define the overall input. So this example of saying, we see two examples. Three examples of an X, two examples of item type Y, two more examples of an X. That says that overall, in aggregate, we've seen a total of 5 examples of X and 2 examples of Y. And again, you can use your imagination, think back to all those motivating applications from scientific data, from medical data, from monitoring telecommunications, from monitoring transactions in an e-commerce store, and think about how that encodes, that can encode the kind of data that you see there. The other example is essentially the same model, but just says we'll also tolerate negative updates. Right, so now in my example, if my third update says -2x, then I get my 3 arrivals of x, my 2 arrivals of y, but then my 2 departures of x. So this is just saying that more generally we can think of items arriving and departing, or increments and decrements, or slightly more, slightly different to that. You can think of what happens if you have one stream that defines sort of one distribution, another stream that defines a second distribution. What you're interested in is the difference between those two. So you're looking essentially at the subtraction from one from the other. And again, if you think back to the invertible Bloom lookup tables and some of the other sort of related things we've seen so far, we've implicitly seen that notion of subtraction, meaning sort of look at the difference and come up with some representation of the difference. Okay. All right, so let's get to something sort of technical. What I'm going to talk about today, I've got a lot of slides and I'm going to try and go slowly and give pauses so if there are any questions or any discussion we can sort of fit them in. I'm going to try and cover a few different results that introduce sketches and kind of tie them in to concentration bounds. And again, we've been using concentration bounds in the last couple of days, sort of taking off the shelf. So I'm going to look a little bit more closely at these bounds, see where they come from and how we can use them. Okay. And we're going to sort of move this discussion along by looking at this concept of the frequency moments, right? These functions of data that I could think of as vectors. Okay. So first, let's take this notion of sketch. I said, I want to think of a sketch as being a summary of a large quantity of data. So I'm going to actually be more specific and say I'm going to think of a sketch as a summary of the linear transformation of data. This word linear is very important. We'll be saying this a lot. Rasmus introduced this in one of his exercises and said, it's important to think about ways of summarizing data that you can think of as a linear transformation. And if this term linear transformation is unfamiliar, what we're basically saying is just we can think of the data representing a vector x and our sketch or summary being computed as some matrix S multiplied by this vector. Right? So I'm saying my notion of a sketch is going to be something that I can write as some matrix S multiplying some data representing the vector x. So why is this a good thing? Well, straight away we can see this has some nice properties. For example, if I'm trying to combine information from different sources, then for any scalars alpha and beta, my sketch of alpha times vector x plus beta times vector y is just alpha times the sketch of x, beta times the sketch of y. So that says, if I've computed sketches in two different places, but using the same transformation, I can immediately compute the sketch of the sum of those inputs. Maybe not as immediately obvious, but reasonably straightforward, is the fact that it also tells us exactly how to incrementally update our summary. Right, so if I say that however I make my summary, it is this sort of sketch of x, of the vector x, then if I see an update in either of those two models, the arrivals model or the arrivals and departures model, I can think of that update as basically being an addition of a basis vector from the standard basis multiplied by its weight. Right? And if I've already got my sketch of the data so far, then to get a sketch of the data with this new basis vector added on, then all I have to do is add on the sketch of the basis vector. Okay, so as soon as I just describe to you what the sketch transformation is, I then describe what is the algorithm for merging two sketches and what is the algorithm for updating with a new piece of information. Okay. So, getting back to hashing, what's this got to do with hashing? Well, the reason is I almost never want to actually write S as a matrix. Why is that? Yeah?
Too big.
Yeah, exactly. Right? If I'm saying X, my data is too big, then a matrix with many rows that multiplies X is going to be way too big. So I don't want to actually write S as a matrix. So it may be convenient for analysis to do so. But I want some implicit description of this transformation. So that this is a worthwhile process, so that I'm really doing something that's space efficient. And the nice thing is, if I can come up with this hash-based description of this transformation, and the hash functions are reasonably simple, then this whole process can be very fast. Okay, and again, picking up the themes that we've seen already, we're going to mostly talk about what's the independence that we need in the hash functions. Right? We're going to primarily talk in terms of k-wise independence, and we've seen constructions, so all I'm going to do is assume that these exist, that they're fast, and questions so far? Okay, so let's make this concrete, because all this talk of linear transformations and high-dimensional algebra can be a bit off-putting the first time you see it. Let's actually take a fairly basic computation and show that we can think of it as a sketch, right? So the first kind of computation I want to do is just say I've got two enormous data sets, one in data center A, one in data center B. They should be the same. Are they the same? So turning that into this setting, I'm going to think of some enormous stream of bits, two enormous streams of bits, and I want to say, are these identical? Right? Is the first bit the same as the first bit in X the same as the first bit in Y, second bit in X the same as the second bit in Y, and so on. Okay. So this is sort of a hashing problem, right? We want a hash function for data that just says hash the data, and if the two hashes agree, then we'll conclude that almost certainly the data agrees over the random choice of parameters that we use to instantiate the hash functions. So we want something a bit different to what you might usually think of a hash function, because here we're not taking a hash of the data as a whole in one go. We're trying to say, let's build the hash of the data incrementally, sort of bit by bit. So as I see a new bit arrive, I want to update my hash of this. And we're going to see, how do we choose this function? So in fact, we've already seen the function we're going to use. It's one that Mikkel used to say how you would hash long strings. So we can go through this fairly quickly to understand why it works. Right, so we're going to pick our hash. Again, nothing scary in this mathematical notation that just says a hash of the whole string X is going to be based on some randomly chosen R in the prime field P. We're going to work over that prime field P to do this polynomial evaluation, where we just add in powers of R to the I. Right? So if xi is 1, we're adding in R to the power I. If xi is 0, we're leaving that term out. We should immediately remember why this works. Why is this hash function going to have the properties that we want, that it's not going to say, it's unlikely to say two strings are the same, when in fact they're different? Okay, good. People are asleep enough that I need to remind them of the short zipper lemma. Yeah?
You look at the difference, the polynomial, how it works.
Yeah. Exactly. So we're going to use properties of polynomials. We're going to look at if two different strings hash to the same value, we're going to look at, well, what does that tell us about a polynomial evaluated on the difference of those two strings? These two strings are different, so their difference is non-zero, but we're going to get a difference of 0 from the hash functions. So what we basically do is we write this function here. We say, look at the function that's the sum over all the indices of the difference between x and y multiplied by sort of this unknown alpha, where alpha is going to be our choice of r. This polynomial in alpha is 0 if the two hash functions agree, but there can't be that many choices of alpha that would make this 0 once we fix x and y. Right? Well, we know that a polynomial of degree n has at most n roots over this field. And if we pick the location to evaluate at randomly, and our field is large enough, then we're unlikely to stumble by chance onto a root that happens to give us a 0 solution. And again, we see this kind of use of this kind of polynomial lemma come up quite a few times, so it's good to be familiar with it. The other thing that's important here about this choice of this function is the way that we put it together. It's a linear function. Right? So that's the other observation. We said we want our sketches to be linear functions. It's linear. What that means is if I look at where the data comes into this, I'm only ever talking about the data multiplying something something else that I can then think of this as a, in fact, this is sort of a vector-vector multiplication, a vector dot product. We're only looking at linear powers of entries of x, we're not looking at the squared values. So we can compute it linearly, we can compute it incrementally as we see the data rise. So, we can step through the analysis, get to the fact that the probability of a chance collision is small if we choose p big enough. And you say, well, pick p bigger than n, the size of the data, but remember, the number of bits you need to represent this prime p, the number of bits you need to do this multiplication over, is just logarithmic in p. So basically, whenever you see you're working over a prime field p that has to be polynomially big in the size of your data, you think, great, that's brilliant. I'm just using logarithmically many bits, this is working really well. Okay. So that's a first sort of linear sketch, just for testing equality. So what's some other stuff we can do with sketching? Well, in order to do this, we need to let's look a little bit at the kind of questions we want to ask. I'm going to look today mostly at questions where we think of the data as representing a big vector x. And what that means is we have some set of items arriving incrementally, and we have this vector x, and I'm going to switch between x and f here. F is that vector of frequencies, number of occurrences of a particular item. And the reason is, once you sort of represent your data as a vector, there's still a lot of interesting questions that you can answer by sort of asking questions on that vector. Right. So, for example, you can say, let me find those entries of the vector that have a large number of values. Right? We heard this sort of heavy hitters concept already. You can say, well, actually, I've seen many, many things. Some I've seen many times, some I saw only once. How many different things did I see? So that's the number of non-zero entries in your vector, right? Also called counter-string quantity. We could look at other functions. So we could look at, say, the sum of the squares of entries in this vector, sum of the cubes, whatever. So these are the frequency moments. They seem a little bit abstract the first time you see them, but it turns out these kind of capture the heart of a lot of the basic questions in streaming data analysis. Right? So in particular, I can write F2, the second frequency moment, the sum of the squares. That's basically giving me the squared Euclidean norm of this vector. So immediately anything that's sort of geometrically related, we're going to need to understand Euclidean norms. I can look at F0, which is, using notation slightly, it's the sum of the fi's to the power 0, so we'll get a 0 if there's a 0 and a 1 if there's a non-zero. So that actually captures back this notion of counter-steam. And I can look at other sort of functions over these frequencies. I can look at entropy. Again, it's going to be some of fi, log fi is with the right scaling. Okay, so we're going to look at these questions. I'm going to see how we can build linear sketch summaries that will let us capture them. And again, this was goes back to a classic paper almost 20 years ago on Matthias and Segedi in Stock 1996, a really influential paper that kind of started this area. So if this is an area you want to work in, then you have to start by reading this paper just to understand how in 10 short pages they kind of laid out a sequence of results that we'd be following in the intervening decades. Okay. So to do any kind of result analysis here, we're going to need some new tools. Right? And the tools we use are mainly these concentration bounds. Right? Because what we're going to do is we're going to look at the algorithms we produce as randomized algorithms. Each algorithm is going to give some output, which we can quite reasonably think of as a random variable. So the output of this algorithm is a random variable, where that randomization, that randomness comes from the fact we're picking different sort of random bits to run this algorithm with. So this is a randomized estimate of the answer that we're looking for. What we want to do is give some confidence bounds on the final estimate x. In computer science, for whatever reason, we want to say that we're close to the right answer with some high probability. Right? So those confidence bounds say how close are we to the right answer, and with what probability, with what confidence do we make that statement. We're going to use these concentration bounds on the random variables that represent the output to argue about the quality of the result. Right. So concentration bounds are nothing that should be that surprising to you. If you've done any statistics, you'll have seen the normal distribution, and you've done all these calculations that work out, well, 95% of my probability mass is within whatever it is, 1.96 standard deviations from the expectation. That's a confidence bound, that's a concentration bound. But that's a concentration bound for a specific distribution. And what we'll be doing here is looking at concentration bounds that apply to arbitrary distributions. So these are all going to look like this. They're going to say, well, we've got some probability of our random variable being, in this case, within some absolute distance to some target value x. Probability of that deviation of the random value from some target value being more than some quantity, call that epsilon y, is at most delta. So we've got small probability of being far from the answer, and what will matter then is, well, firstly, how we're choosing these x and y values, how we're making this probabilistic statement. And often, what we'll actually be doing is saying, well, x is going to be the value that we want, that frequency moment. Y is going to be some, maybe multiple. Epsilon y is going to be some small fraction of that the value we're looking for, so it's going to say we're sort of within some relative error of the target value. Okay. So, let's build a concentration inequality. Start at the basics, the Markov inequality. I think we've used it once or twice so far, but I think it's instructive to actually build it from scratch. Right, so we'll take some probability distribution. So it's a distribution over numeric values starting at 0. I'm going to enforce the constraint that there's no probability mass below 0. So I have my probability distribution, has some strange weird shape, and somewhere in this probability distribution I have some value k, and I'm just going to try and work out, well, what's the probability that I have, what's the probability mass to the right of this value k? The idea being that most reasonable distributions, you're going to have some large amount of probability mass sort of in this initial fraction, and as you go further to the right, you get less and less. Can we reason about that? So what we'll do is we'll set up we'll set up a random event. Okay. Set up a random event x that corresponds to, or rather, our distribution rather is going to be this, we're going to call x. We're going to think about the event that x is bigger than k. So we want to start reasoning about what's the probability x is bigger or equal to k. Well, let's just look at that event, and let's look at this quantity, k times the indicator variable that x is bigger or equal to k. So what that means is if x is less than or equal to k, I get 0. So if x is less than k, I get 0. If x is greater or equal to k, this becomes 1, and so I get a contribution of 1. And what I'm going to say, sort of a little bit hand-wavily, is that this quantity is less than or equal to x ready for all of x. Well, that means if I pick x and it's bigger than k, greater or equal to k, then I get something greater or equal to k on the right-hand side and k on the left-hand side. So the left-hand side is smaller than the right-hand side. Or I pick an x which is less than k, so I get something less than or equal to k but greater than 0 by that requirement. and on this hand, on the left-hand side, I get 0. Okay, so I'm sort of saying these two things obey this inequality, and what I can then do is just take the expectation of both sides. So I can look at what is the expectation of k times the indicator variable x greater equals k, and say that's less than or equal to expectation of x. Okay. So expectation of x is something hopefully I'll know something about, right? Saying I have a probability distribution. If I know nothing else about this probability distribution, I should at least be able to work out the expectation. This quantity, right, so I then start just applying my basic rules. So I know that expectation of a constant times a random variable is just k times expectation of the indicator variable x greater equal to k. And the expectation of the indicator variable is saying, well, what's the probability that this is 1 times 1, plus what's the probability that this is 0 times 0. So that just gets me k times the probability of this event. Less than or equal to expectation of x, and that is basically the Markov inequality. Right. So what this Markov inequality tells us is that we're unlikely to radically exceed the expectation of a random variable. Okay. Probability that a random variable exceeds k times its expectation is at most 1 over k if we just sort of reorder things a little bit. And when we write it in this form, it's relatively weak. Right? If you look at the kind of distributions that you see in the world, if you look at a normal distribution, if you look at a Zipfian distribution, then this is much weaker than the kind of bounds you can actually state about that variable. But I'm going to say that nevertheless this is still useful. It's useful for a number of reasons. It's useful directly in this form, and it's useful because it's actually how we show every other concentration inequality. So let's go to count-min sketch. This is something Michael introduced on Monday. We'll look at it again today because it really is just the instantiation of the Markov inequality applied to the right random variable. Okay. So again, we're thinking about data as being represented by a vector x of some high dimension u. And we don't want to represent it in such high dimensional space. We want to represent it compactly in some small summary. So think of the summary as this. Right, let's see if I can work with this. Brilliant. Think of this summary as an array of W times D entries. And again, this is sort of the same thing we've been seeing with partition Bloom filters, or partition hash tables. Right? Each of these is basically a hash table, and each of these rows or hash tables is accessed by a different hash function. So we're going to use D different hash functions to map entries of x into each row correspondingly in the following way. Very straightforward. We have a new arrival, a new update indexed by j with a corresponding update mass c. So think of sort of c as the arriving weight of that element. We're just going to hash j in each row, the different cell, and add in that weight there. Okay? So kind of like a Bloom filter, but instead of just setting things to 1, we're keeping a running sum of all the mass of elements that are mapped to that cell. And what we're going to do is say, right, when we've done this, we've mapped our huge vector down d different times to d different d different rows. And I'm going to claim that nevertheless, even though there's been lots of collisions, lots of masses piled up together, there's still enough information here to kind of reconstruct the peaks in that original vector x. Right? So what we're going to do is we're going to go and look at that vector. We're going to look at, for a particular index j, where that index j maps into this structure. Look at all those locations. In each location you have the true value of xj at that location, plus some noise, some entries from elsewhere in the vector that collided under that hash function. So if we assume that the vector has only non-negative entries, and I think I put up some exercises that say remove that assumption, but now we'll assume that that entry has non-negative entries, then what you can say is, well, you know, in the first row I've got the true answer plus some noise, the second row I've got the true answer plus some noise. If I want to minimize the noise, let me just look for the minimum of all of those locations where my index J mapped. And let me reason about what is the error that I get. So what I can do is set this up as a problem with a random variable and analyze that random variable. So in row, how do I do this? It's K. In row K, I've got a random variable xk that's equal to, when I look up for the jth entry, equal to the jth entry of the vector, because I know it hashed there, plus the noise. And that noise is just the sum over all I not equal to j, such that the hash of j, hash value of j, is equal to the hash value of I, xi. So what I want to do is understand how far does this random variable deviate from xj. So actually, let me modify my definition. Let me just say that xk is now the noise. So I'm just looking at the noise, taking away xj, the value that I want to estimate, is just the sum of items colliding with it. Okay. So this I can actually write as just the sum over all I not equal to j of the probability that these two hash values collide times xi. Okay. Because this is something I can reason about easily, right? Let me pick my hash function to be any pairwise independent or universal, you know, whatever terminology I want for this hash function, right? That says that I can treat the probability of a pair of collisions as being uniform, of a pair colliding as being uniform, right? So if I fix one cell and say what's the probability that any particular other item collides in this cell, just 1 over the number of cells.
So you now move to the expectation.
I'm not yet in the expectation. I'm going to take that in like one more step.
No, but so how? Then why do you have to call?
Oh, yeah. Yes, yeah. You're right. Yeah, I've jumped to taking the expectation of this. Thanks. Sure. So I'm looking at, well, how big is this noise? So you're right. I'm looking at the expectation of this. So then I have this summation of probabilities, and this probability is just uniform. So I now have the sum of I not equal to j, 1 over w times xi, and I can just say that this is 1 over w times the sum of the xi's. I can even drop this requirement, it doesn't change things massively. And just say it's 1 over w times the sum of entries in vector x, which I'll write as a 1 norm of vector x. So for a single estimate in a single row, I get a reasonable expected noise, but the amount of noise I might actually get is much larger. You can imagine, what if there's some really big entries? If I'm unlucky and I collide with those really big entries, those could be a lot larger than what I expect. So then what I do is I just pull out the Markov inequality and say, what's the probability that xk is greater than, let's say, twice the expectation And immediately I say, actually, I'm going to be unlucky. I've got, at least half probability that the noise that I get on a single entry is more than twice what I expected. So I could be quite unlucky several times. But if I take the minimum of all of these estimates, then the probability that all of them are bad, the probability that all of them are large, is going to be, so if I take the probability of min over k, that's going to just multiply up. So if I take the minimum over d repetitions, the probability that all of them are bad is 1 over 2 to the d. Okay. So why can I make that argument? It's because each row is completely independent of every other row. Right? I'm using a different hash function, so I don't have to worry about dependencies across rows. So again, this is another sort of trick that comes up quite often. You're using bounded independence in one place and reasoning about what you can get with bounded independence, but then use independent repetitions to kind of amplify that probability of success. Okay. So what this says, if I do this whole process, then it's fairly cheap, right, to get this probability very small. Right, to make this, 1 in a million, I just need d equals 10. Right. So I kind of rewrite this on the slides. So the slides have sort of essentially the same analysis worked out. I can rewrite this by choosing how I pick my w for the width, d for the depth of this table of hash values. And say if I pick, w is, say, 1 over epsilon, d is log 1 over delta, then I get this kind of epsilon delta guarantee that says my error is at most epsilon times, here I've written as f1, the sum of the weights, with probability at least 1 minus delta. Any questions? Okay. So this gives us sort of a primitive data structure, a primitive operation that lets us pull out heavy entries up to some additive noise in the mass, the 1 norm of the vector that we're summarizing. And you can start thinking about, well, how can you plug that into more complex questions to let you answer those? For example, one thing you might want to do is say, can you find those indices I where the corresponding weight is large? Can you find the i's such that fi is large? More than some constant fraction of total mass. So a slow thing you can do is you can just sort of either enumerate all possible indices and use the sketch summary to give an estimate for each of those. And then, that works. You have to be a little bit careful with the probability, use a union bound to bound probability of failure, but that will work fine. Or, you can kind of do it online. If you're doing this process and updating information, you can just probe the sketch every time you look at it to pull out an estimate of the weight of that element. But you can start thinking, put your algorithms hat on and say, well, can I do something smarter? So the natural thing to do is say, well, if I can estimate the weight of a single element, I can also use the same trick to estimate the weight of groups of elements. So what I can do is think about putting a binary tree over my input domain, conceptually, so that any node in the tree corresponds to a subset of elements. And then the weight associated with that node tells me sort of the sum of those weights. And then I can essentially do a search procedure. I can do a binary search through this tree to find where all the heavy leaves, corresponding to heavy elements in the original structure, by just saying, well, a heavy leaf must have every ancestor heavy. And so I can just do that search and discard branches that are light. And I can also argue that I'm not going to waste too much time doing this search because I can't have too many heavy things at any one level. Okay. So I mentioned this for a couple of reasons. One is to say, once you have these kind of sketch summaries, you can start using them as black boxes and building more complicated things around them. And the other reason to mention it is that this kind of question, can you find the heavy entries in a vector, is very connected to this area called compressed sensing that's had a lot of activity in the last decade, coming from signal processing, coming from the statistics world. But the basic question being asked in compressed sensing, once you get past all the terminology, is, given a vector, can you design a sketch so that you can find the heavy entries in that vector? And there are a few more twists, because maybe you have both positive and negative entries. You want to get your probabilities of errors very, very small, almost exponentially, vanishingly small. But nevertheless, these kind of simple combinatorial constructions also get you an insight into these statistical questions. Okay. Another application of this that I'll mention very briefly is in machine learning. So in machine learning, you're dealing with objects which are represented by features. And one of the trends in machine learning at the moment is look at objects that have a huge number of features. You have many objects, each with a huge, sparse feature vector, such that it's quite slow and costly to run your machine learning algorithm in this high-dimensional feature space. And what you can do instead is say, well, rather than work in the original high-dimensional feature space, why don't I build a sketch of my object and sort of run the machine learning algorithm on the sketch rather than run the machine learning algorithm on the original data. This seems sort of odd, seems to work well in practice. There are sort of technical reasons why. I'm hoping John Langford will be here tomorrow to explain why. So let me go on a little bit further and say, well, what can we do? Because in some ways the Kaplan sketch result is sort of interesting, but when you pull it apart, you can kind of see, okay, there's some big spikes in the data. I should be able to find them just by hashing down reasonably effectively. So let's do something that I think is quite unintuitive the first time you see it, and look at F2, which is the sum of squares of entries in the vector. So in order to have anything to say about F2, we're going to need a new, stronger piece of technology. So let's take the Markov inequality and kind of soup it up a little bit. So I said already, Markov inequality on its own is relatively weak because it's not making any assumptions about the distribution. Right? You can build distributions that kind of, in a worst case sense, achieve the Markov inequality, and they look pretty unnatural and not like any distribution you normally encounter. But what we can do is take the Markov inequality, and it applies to any random variable. So in particular, it applies to a random variable that's a function of another random variable. So I can take my random variable x that I'm interested in and apply some function, some transformation to x, and apply Markov inequality to that transformation and get a statement about that transformed version. Okay. Why would you do that? Well, here's sort of an example why. So let me think about my random variable x, and let me define a new random variable y that's the square of the difference between x and its expectation. And this should not look completely out of nowhere, because this looks kind of like the calculation you do for the thing you do to define variance. Okay. So I can say by the Markov inequality, the probability that y is greater than k times its expectation is 1 over k. Okay, that's immediate. So let me now sort of plug in what y is in terms of x. What's the expectation of y? It's the expectation of the deviation of x from its expectation, all squared. That is exactly the definition of the variance. So the expectation of y is the variance of x. So what this says, just substituting back in, is the probability that the squared deviation of x from its mean is greater than its variance, is at most 1 over k times its variance, is at most 1 over k. Let me just sort of rearrange that. So let me do one more trick and say, well, let's take that statement and take the square root of everything inside the probability statement. So the square root of x minus its expectation squared is the absolute value of the difference between x and its expectation. So we're saying the probability of the absolute deviation between x and its expectation is then the square root of what was over here greater than the square root of what was over here is square root of k times its variance is at most 1 over k. And again, I might rescale to get this in a more convenient form. So I'll just say the probability that x deviates from its expectation by more than some absolute value k is at most the variance of x divided by k squared. I got that just by rearranging and redefining what k was. Okay. So that's the Chebyshev inequality, which we've, I think, invoked once over the past couple of days. It's the Markov inequality applied to the right random variable. And this is kind of useful because it says if we can make the variance of x small, if we can make the variance of x very small compared to, say, the square of the expectation of x, then you're substituting that in, it says we'll have constant probability of being, we'll have only a very small constant probability of sort of going even a little bit far from the expectation of x. So why is that useful? It's basically because the variance of a random variable x is something that we can manipulate, right? So if I have a random variable which has high variance, one trick I can do is I can repeat that process. I can take multiple independent draws from the distribution generating that random variable and take the mean of those. And we understand that the mean of this repetition of draws from a random variable shrinks the variance, right? So we know we have a tool that will let us get small variance so long as we've got a variable which has reasonable variance to begin with just by taking repetitions. So this is looking promising. This is saying we can as long as we can make statements about the variance of a random variable, then we may be able to make good concentration bounds from it. Okay. So let's do this for a new sketch. And this new sketch is going to look very much like the last sketch. This is the AMS sketch, because we call it that because of Alon, Matthias and Segedi proposed back in 1996. We're going to use this to allow us to estimate the second frequency moment, the sum of squares of the entries in this vector. It's interesting in and of itself, but also interesting because it gets used in lots of different ways in lots of other streaming algorithms. Now I'm going to describe it in terms of just taking the CM sketch, the Countman sketch we've already seen, and making one change. So what we're going to do is take an extra set of hash functions, some G hash functions. So before we had H hash functions mapping us to a location in each row, we're now taking a second hash function G, also one for each row, that map each entry of the vector x to either a +1 or a -1. And if you want to impress your friends, you can say, yes, so this is realizing low independence Rademacher variables, because it's a fancy way of saying you either get a +1 or a -1. And the way we use these low independence Rademacher variables is when we have an update, we again hash to a location in our collection of cells, we add on the update value, the updated weight C, we multiply it by either the +1 or the -1 that we get by hashing the element in question. Okay. So same picture as before, we take an update J, we hash it to some location in the first row, and we add on the weight of that update multiplied by the G hash, the first G value hash function of that index J, and so on. We're also going to have a larger array here, and we'll reason about how big this array needs to be. Okay. So before with the Countman sketch, to make an estimate of a single entry, we looked at the locations where it hashed and took the minimum of those. To make an estimate of the hash for second frequency moment, we're going to do something different. In each row, we're going to look at the sum of squares of entries in that row. So we wanted to look at the sum of squares of entries of the whole vector. We're going to hash down to this small space and look at the sum of squares of entries of each row. And then we're going to get a different estimate for each row, and we're going to take the median of those. So we need to understand two things. One, why is this sum of squares in a row getting a random variable that has some relation to the sum of squares of entries in the original sketch? And two, why are we doing this median operation? Okay. So this is where one needs to just start sort of, again, doing this kind of calculation when you get more variables, more collisions, because more things are going on. Right. So I look at what happens in a single bucket, in a single cell in this sketch. when I take the square of that cell, I can reason about, well, I'm looking at essentially the square of the sum of the elements that hash there multiplied by these g values. When I multiply that out, which is not that difficult, I get something that looks like this. Right? I get the sum over, and then if I take the sum over all buckets, I sort of get this larger sum. So here I've got the sum over all buckets. I've got my terms that come out of this summation when I just look at what this random variable is giving me. Is I get the sum of all the entries in the original vector squared, because they all land in the same bucket, squared, and I get a term multiplying gi, the hash value of I squared. Plus I get essentially all those cross terms. Right? I get the cross terms that come from every time I get xi and xj landing in the same bucket. So I'm saying only those I and j such that they hash the same bucket, hash of I is equal to hash of j, do I get the cross term of xi times xj times these hash values. Okay. So why does this have any chance of working? It has any chance of working because of this term here. Right, gi squared, what's that? Stop. Yes, very good. So gi squared, we know that gi is either plus 1, in which case gi squared is 1, or gi is minus 1, in which case gi squared is 1. So this term here gives the sum of the squares of the entries in the original vector, f2, that's what we want. Right. If that was it, then we'd be done. We have all these cross terms to handle. Right. We have some hope of doing something here, because if I look at what can happen with these cross terms, I've got 4 possibilities. I either get a plus and a plus, plus and a minus, minus and a plus, a minus and a minus. So I multiply those out, and I either get plus 1 half the time or minus 1 half the time, provided these hash functions are such that these pairs are uniformly distributed. So provided this hash function is at least pairwise, then the expectation of these cross terms is 0. Okay. So kind of you do this hashing trick down, multiply things out, sum the squares up, and what you get is something that gives you this sum of squares of entries in the original vector in expectation. Okay. But we know sort of somehow that it's never going to be quite that simple, because although the expectation of this error term is 0, so half the time it's some positive thing and half the time it's some negative thing. So although it's 0 in expectation, it's going to go off in other directions. We need to look at the variance of this to bound. How far away are we going to be from the expectation? Okay, so we have the expectation of our row estimate is exactly f2, so I'm going to call that random variable after k. Well, what we'll do is we'll look at the variance of that random variable in anticipation of applying Chebyshev inequality. Okay. So we look at the variance, and that variance is sort of the expectation of the square minus the variance is the expectation of the square of the difference between the value and that's expectation. So you get this thing here, and if you start expanding this out, you initially start to wonder if this is the right thing to do, because you start getting all these cross terms, you run out of space on the sheet of paper you're writing on. But it's a good exercise to go through because it does simplify considerably. And the reason it simplifies is you expand this out, you're looking at sort of the square of a square, so you're looking at a polynomial of degree about 4. So you've got a bounded degree of terms that you're looking at here. And the kind of terms you get, are some g value of one element times a g value of another element times a g value of another element times a g value of another element. And we're going to argue that most of those terms go to 0. Okay. Because what we're going to do is make a stronger assumption, not just that this hash function g is pairwise independent, but actually that it's fourwise independent. So it's behaving uniformly over subsets of size 4. We're getting lots of terms that have subsets of size 4. We're just going to reason about how do they impact this probability calculation. Okay. So why can we start simplifying this? It's because when we looked at the expectation, we could argue that some terms went to 0. When we look at the variance, which is also an expectation, but in a higher degree, we've still got terms that go to 0, and these ones, again, you can treat as going to 0. So any term that looks like, g of a times g of b times g squared of c goes to 0 because we have an odd power of g here. So we just look at the impact of this term. Half the time it's +1, half the time it's -1, so that goes to 0. Anytime you have all different, that goes to 0. Anytime you have odd powers, they go to 0. So you can get a bit enthusiastic here and say, oh look, the variance goes to 0, but that's not true because you have to realise that some terms remain. Right, the terms that remain are those that involve even powers of this hash function. You can't get rid of those that easily. So you simplify and simplify, and you get down to something, a statement of the variance has a few terms with even powers. I won't go through the details here. I'll leave that to you. You simplify those, and then you look at, well, what terms are left. And what's left is something in terms of the square of f2. So the sum of the, essentially these terms here, xi squared, xj squared, times the probability that those two I and j ended up in the same bucket. So you end up with the square of f2 divided by w, the number of cells. Okay. And that's exactly what you want. Right? You can bound the variance of your estimator in a single row by f2 squared divided by w. And this is important, because this is a variance, and we actually have a handle on this variance. We have a control, w, that lets us say, oh, is this variance too big? Okay, let me just make w a bit bigger. I'll make that variance smaller. So I plug this into Chebyshev, and I use that to set what value of w I want. And basically, if I set w something like 4 over epsilon squared, then it says the probability of a single estimate from a single row being very different to what I'm looking for, f2, being more than some small epsilon squared fraction of f2, is at most a quarter. So that says with a single estimator from a single row of this structure, I have good probability, a small constant probability of being mistaken. And now it's a question of how do I amplify this, right? I want to get this small constant probability of a quarter down to 1 in a million, 1 in a billion. So the first thing I could do is I could say, well, I have this dependency on w. What happens if I play with w? And that gets you so far, but not very far. So I can play with w, make it a little bit bigger, make it say double w, and I'll halve that failure probability. But I'm impatient. That's not getting me to a small probability fast enough. Right? So rescaling w only linearly impacts this failure probability. Whereas with something like count in sketch, I said, oh, I'll just do a few more repetitions, independently different rows, and take the minimum, and I'm sort of exponentially improving my failure probability. So I want to do something like that. I want to say, well, let me just take a few more repetitions, and then sort of combine them to get a single estimate at the end, and argue that this is going to drive down my failure probability exponentially. So the problem is with count in sketch, we had this sort of one-sided error that said I could just take the minimum, and that would sort of move me towards the best estimate. With this, I've got two-sided error. I have some estimates that might be too large, some estimates that might be too small. How am I going to sort of figure out which of those I should, how I sort of navigate within them? So I'm going to make use of a new trick. And to do this, I need some new technology. I need a Chernoff bound. So again, we've already seen Chernoff bounds in our exploration so far. And we just said, let's go to the textbook, pick out a Chernoff bound, and run with it. So I believe in building things myself, or at least understanding what it is that I'm using. So we're going to make a Chernoff bound. The Chernoff bound is nothing more than the Markov inequality applied to the right function of a random variable. Okay. So let's set up the scene. So I'm going to make life easier for myself by looking at a nice simple Chernoff bound. So we're going to look at a Chernoff bound applied to independent Bernoulli trials. Right. What that means is I'm tossing a coin that comes up heads with probability p, and and I want to reason about what's the number of heads that I'll see compared to the expected number. So I now have my random variables x1 through xm are my m independent coin tosses. And again, to make life easier for myself, I'm going to say that these are all the same. So they're sort of independent tosses of the same coin. So the probability that my coin comes up 1 is p for every coin. Probability that it comes up 0 is 1 minus p. So, you think of sort of zeros as failures and ones as successes, or vice versa. And we're going to see how many successes do we get compared to how many we expect. So let me have my new random variable x just be the summation of all of those. And let mu be shorthand for the expectation of x. So m times p should be mu. Okay. So what I want to do is look at what's the probability that my random variable x is more than, say, some small 1 plus epsilon times mu. Right, so mu is what I expect, and I want to say let's say what's the chances that I get much more than I expect. And the way we apply this, we want to say we're hoping we're not going to have much more than what we expect. Okay. So here I'm going to plug in a transformation, and for whatever reason I decide that the transformation I want to do is take an exponential on both sides. So I'm taking this exponential function, exponential of t times x, where t is a constant that I'm going to set during the analysis. Okay. So this probability is the same as this probability because, the chance that this is greater than this is the same as this because this is the right kind of monotone transformation. Okay. And then I apply the Markov Inequality to say, well, the probability that this random variable is greater than this value is at most the expectation of that random variable divided by that value. Okay. So in order to make any headway, I need to understand what is the expectation of this random variable, which is this random variable x multiplied by t exponentiated. So let's look at that. The expectation of that random variable, well, x is a summation of random variables. So I'll just expand out, use the fact that I understand how the exponential function works, and do a little bit of, use the fact that the xi's are independent, to say that this expectation of this function is the product of all those in this case exponential function of t times xi. Okay. Right, just using independence and properties of expectation. Okay. So now let me look at what is the expectation of this term here. Well, actually, this is quite easy, because xi takes on two possible values. Either xi is 1 with probability p, or xi is 0 with probability 1 minus p. So I can now happily say that the expectation of this is p times what I get when xi is 1, which is e to the t, plus 1 minus p times what I get when xi is 0, which is 1. in fact, I now have the product over the different i's of p times e to the t plus 1 minus p. And then, here's sort of the only trick that we need here. I want to make my life easier for manipulating these things. So I'll upper bound this quantity here by this. Okay? This thing in here, p times e to the t plus 1 minus p, I'll write as e to the p times e to the t minus 1. And the way I get that is just by using the fact that I remember that, x with x is 1 plus x plus squared over 2 plus all that stuff. And basically, if I expand that out and I expand that out, I'll see that essentially this has all the terms I have here plus a few extra. So that inequality works. Okay. So now I'm looking at the product over m things of this quantity. So then I just plug that in and say this is essentially e to the m times p times e to the t minus 1. And since m times p is my expectation, e to the mu e to the t minus 1. Okay. So that is my term up here. I've managed to say this expectation I can write is at most this. So I'll substitute this in. And so I've got x mu e to the t minus 1 over x mu t 1 plus epsilon. There. So just bring this across. And that, I can kind of again bring these two terms together. Mu, whatever this is, e to the t minus 1 minus t. And that I can basically just write out is x less than or equal to x mu t squared over 2 minus epsilon t, where this step I basically again plug in the definition of e to the x to jump down here. Okay. So then the last step that I need to do is say, well, how do I set this t value so that what I get is going to be useful? What I basically do is I sort of look at these two things and say they should be dimensionally the same. They should both be sort of in terms of the same kind of quantity. So I just think about this for a bit, and I set t equals epsilon over 2, and I get this to be x minus mu epsilon squared over 2. Okay. So when I look at what that's done, when I put it all together, I said the probability in this situation with these Bernoulli random variables that x is more than 1 plus epsilon times its expectation can be bounded in terms of exponentially small in that expectation times epsilon over 2. Epsilon mu epsilon squared, yeah, over 2. Okay. So I have that inequality, and what that's basically saying is I can sort of say that this probability of being far from my expectation, being much larger than my expectation, gets really small really quickly for the right settings of mu. Okay. So that's the kind of Chernoff bound that I want to use. Let's plug that in and see where it gets us. Okay. So firstly, why on earth was I doing that? What's that got to do with the thing I was doing a few minutes ago, looking at sums of squares of values? Well, what I basically wanted to say is I've got an estimate for each row that's a good estimate, probably. Right? With 3/4 probability, this is a good estimate. And so what I'm going to do is take the repetitions of this estimator And I'm not going to look at the min, because that might be too small. I'm not going to look at the max, because that might be too big. So I'm going to look for something in the middle. I'm going to look at the median. So why the median? So if I look at these repetitions, so think of them as just balls placed in a row, and I sort of sort them from smallest to largest estimate, then the smallest few estimates might be bad. The largest few estimates might be bad. Right? So the smallest ones might be too small, the largest ones might be too small, but in the middle, I should have the good estimates. Right? If I sort these estimates, the good ones will come in the middle. And if I take the median of these estimates, then in order for that median to be bad, I've got to have been really unlucky. Right? I've either had to have a large sequence of small estimates be bad, so that the median now becomes too small, or a large number of large estimates be bad, and so the median becomes too large. So the good estimates are sort of forming this contiguous group in the middle, and in order for the median to be bad, at least half of them must be bad. And this is where I can plug in that Chernoff bound, because I'm saying with probability 3/4 these are good, so with probability 1/4 I've got a bad estimate. And I need at least half of my estimates to be bad. So I've got a lot more bad estimates than I was expecting. So I'll be able to take this and say, let's X be the number of bad estimates. I expect 1/4 of them to be bad. If I see, more than twice as many, that's going to be really unlikely. So I plug that in. I plug this in with D independent estimates, probability of P is 1/4, look at the probability that I have more than D over 2 bad estimates, and I can say that gets exponentially small as a function of D. Right, so the more estimates I take, the less and less likely it is that the median of those estimates is going to be bad. So I'm going to set D, the number of estimates, now only has to be logarithmic in 1 over delta, my target failure probability. Give me this delta probability of failure. Okay. And again, I took some time going over that, went through the Chernoff bound, because actually this outline is used time and time again in streaming, sketching, summary construction. You build an estimator, you show that it's good, you bound its variance, or give some other way of arguing that it's good with constant probability, and then you take a few repetitions of it and do something like the median or the min to amplify that constant probability up to really high probability of success. So this gives us a way to estimate F2, or if you think like, you think of it as L2, the Euclidean norm, because if you have an estimate of the sum of the squares, you can take the square root of it, and it'll be a pretty good estimate for the Euclidean norm. And it says that from a sketch of size 1 over epsilon squared, I'm getting relative error epsilon on this estimate of the length of this vector. And this is a vector I'm only being told about incrementally, I'm only being told updates to each entry of this vector, and yet somehow I can do this. And once I can do the Euclidean norm, I also have a way of looking at something like the dot product between two vectors. So directly, I can say, well, because I can write the dot product in terms of the squared norms of two vectors x and y, I can rearrange to find an estimate of the dot product. I'm not going to get this with relative error. Indeed, dot product is basically an example of a fundamentally hard problem where there can be no sketch that will get you a very highly accurate estimate. But you can get one where the error scales with the product of the norms of those two vectors. And in some situations, that's good enough. I can then take that dot product result and say, well, if one of those two vectors that I'm taking the product with is a basis vector, right, it's 1 in location j and 0 everywhere else, then that basically, the dot product picks out a particular entry of vector x. So I get a different way of doing a point estimate, where my error guarantee looks like epsilon times the Euclidean norm of that vector. So this sort of version of AMS sketching, sometimes called the count sketch, because it was sort of directly proposed under that name. That says this is a way that you can estimate a single entry of the vector with probability epsilon times the 2 norm of the vector, compared to the count min sketch where you get an estimate with epsilon times the 1 norm of the vector. Now usually the 1 norm is larger than the 2 norm, but you pay more to get that 2 norm estimate, so they're a bit incomparable. And a forward pointer I'll say that all this stuff you can think of as a low independence realization of the Johnson-Lindenstrauss lemma. Right? So I think Alex is going to talk more about dimensionality reduction in geometry. So he's going to talk more about Johnson-Lindenstrauss, which is essentially a way of saying you can take a large vector and you can reduce its dimensionality. It's not exactly the same because Johnson-Lindenstrauss results say that rather than do this sort of strange thing where you look at the Euclidean norm of a few different sort of vectors in your sketch space and take the median of them, the Johnson-Lindenstrauss norm says actually you can do this in a way that you can directly take the Euclidean norm of a sketch vector and get a good estimate for the overall Euclidean norm. And that's powerful because that says essentially you can do dimensionality reduction and you start in Euclidean space and you move down to a much smaller Euclidean space. So then you can take any algorithms you have that work in Euclidean space, run them in that map down Euclidean space and get approximate answers. So in some ways Johnson-Lindenstrauss result is stronger, but in other ways the results are a little bit weaker in that you need a stronger, you need more independence in your hashing, and you need essentially more, you have a denser transformation. Here, if you look at this transformation, you look at how does one element in the original vector get mapped? It gets mapped very sparsely. It gets mapped only d times, whereas in the Johnson-Lindenstrauss results, these transformations are a bit denser, and as a result, they're a bit slower. So I think that's probably a good point to pause, have coffee. I think there are posters outside. So I'm going to stop there for today and maybe talk more about F0 tomorrow.